Okay, so let's suppose that our subgroups are actually very meaningful. Well, what the implication would be then is that the variance within the group, so the spread around these subgroup means, would be small. So the within groups variance would be small, and then the remainder, the leftover, the variance, the difference between this sample mean and here, the variance between the sample means and the overall variance would be large. So we call this the within groups variance, and then the rest the between groups variance. So if our groups are meaningful, the within groups variance would be small, and the between groups variance would be large. Now let's suppose that our subgroups aren't meaningful. So they don't, the data is not really different across subgroups. Well, these x's would look basically the same. So they would be equally spread across all of these. All of these blue x's would roughly look the same as the green x here. And so the within groups variance wouldn't be, so the variance within group 3 would be virtually the same as the variance of the sample as a whole. So in that case, the within groups variance would be large, and the between groups variance, the leftover, would be very small. In that case, we would not say that these subgroups are meaningful, and therefore, and that would return a test statistic that would fail to reject the null hypothesis. So the test statistic for ANOVA compares the ratio of the between groups variance and the within groups variance. So we want the variance within groups to be small. We want our subgroup means to be very predictive of the data. So if these x's were tightly packed around x3, and these are around x2, and these are on x1, that would be good for suggesting that these groups are meaningful. And again, the reason to do this and the nice way to approach it this way is that there's no limit on the number of groups. I mean, or at least the limit is not 2. The number of groups should still be relatively small, but we can do something more than 2. So again, so the result is if we have statistically significant amount of variance explained by the subgroups, that results in a rejecting the null for the ANOVA. So ANOVA compares means from multiple groups more than 2, but it also doesn't enforce a relation between them. So in next class, we will be studying regression, where you have two variables of interest. Two groups of interest, and the relation. Let's see. So the regression forces a linear relationship between the variable we're grouping by and the mean in general. And that while regression doesn't force you to group, actually, so you have a linear relation between a continuous variable and a continuous variable. Whereas ANOVA, it doesn't necessarily have to be linear, but you have to constrain your variable to be a particular number of groups. So for example, we can think about, well, maybe decor is different across 4 different cost categories. So maybe the cheapest restaurants have lousy decor, but then the top 3 restaurants basically have similar decor. So that type of question doesn't enforce a linear relation between decor and cost category. They're all allowed to freely move, and the ANOVA simply asks the question, well, is decor different across cost category groups? In a regression, we would say, as decor goes up, does cost go up? Do those move together? And we wouldn't have to break cost into groups, but we would be forcing a linear relation. So, we can do an example. So let's break restaurants, the restaurant data up into 4 cost categories and decide whether there's a difference in food quality across these categories. So step 1 will be to generate a grouping variable, and we will do that in Excel and then open it up in PISW after we've generated the groups.